Hello, my name is Daniel, and today I'm gonna talk about how we in GlobalLogic use machine learning to identify and classify cancer nodules in lungs based purely on raw CT scans. Okay, so the problem we are facing, or that our client is facing, is that this is how one slice of a CT scan looks like. The complete CT scan is composed of tens or hundreds of slices like this, and the radiologist spent like literally hours trying to find and inspect these white spots because some of them could be cancer nodules that are malign and potentially dangerous for patients. So obviously this process is very tedious. It takes a lot of time and effort to find the smallest nodules, and the way it is done introduces a lot of space for making mistakes. So these are the issues that we're trying to address with our software prototype. So once again, the task is to find and classify cancer nodules based purely on a CT scan. Yeah, so before I dive into the technical part, I want to tell you a little bit about processes. So what we use in GlobalLogic and what's the industry standard is basically CRISP-DM, which stands for Cross-Industry Standard Process for Data Mining. And it consists of 6 parts. The first one is understanding the business problem we are going to solve, so that when eventually we have our solution, it's just gonna fulfill all of the requirements of our client. You have to realize that the accuracy might not be the only factor that the client might be interested in. Very important is model transparency, speed, how fast can you get your predictions, how costly are those predictions going to be, and yeah, that's pretty much it. So in the next step, you want to basically understand how your data is created and how it gets from the point where it was created to you. Because there are many possible options how the data could get messed up along the way. It could arrive in wrong order. Some parts of the data could be missing. There could be errors in manual data entry, and you have to think about all of these and manage it in some way. Okay, so once you have the data, or at least you think you have your data and that you understand them, you can start with data preparation for your model, and that includes a lot of pre-processing, normalizing, handling missing values, stuff like that. I think the data preparation is the most boring, but also the most important part of a data science job, because it works on a principle shit in, shit out. I mean, it doesn't matter what algorithm you use. If you just don't have the right data, you won't have good results. So you should spend most of your time in this first part of the graph, data understanding and data preparation. Once you have your data prepared, cleaned, and everything, you can actually get your hands on machine learning and neural networks and the cool stuff. And then it often happens that your data were not prepared correctly. So you have to go back, and this is not a strictly linear process, as you can see on the picture. Sometimes you just have to go back and then continue and maybe then go back again, but it's just normal. It's part of the process, and you really should do that. So once you have your model ready, at least in some form, then you can go on and evaluate it. Evaluation is not just about accuracy. It's also about how many false positives you had, how many items you misclassified, and also how much time does it take to make a prediction, how much time you need for retraining your model, maybe how much transparent is your model, and these are all the things that you have to account for. One very rarely discussed thing is something called ML fairness, which is basically about analyzing your models for different subsets of your data set. For example, if you have a model for predicting credit score based on some features, okay, you might have a very good accuracy in general, but actually you might discover that your model is not fair, doesn't work well for some very specific subsets of your data. I mean, I don't know, I don't want to offend anyone, but you might find out that like your model doesn't work well for Asians aged between 35 and 40 years, but it works well in general. So you have to account even for these specific subsets and do your analysis. Yeah, and once you have it, you can actually deploy it in use and build all the monitoring stuff and online learning. And then, yeah, you can usually iterate on it, because once you get more data, you get more information about the whole process, and it just continues. Okay, so how we actually started and approached this problem. So we went to Kaggle. Kaggle is a platform for predictive modeling. It has a lot of users now. It was acquired by Google lately. But why we went there? Because in 2017, there was a competition held named Data Science Ball. It was focused on analyzing CT scans and deciding whether they contain cancer or not. The data set was not particularly useful for us, but on Kaggle there are also kernels where people share their code, and we're quite inspired in areas such as segmentation of lungs and segmentation of nodules, and also about what are the standards in working with CT scans in Python. So then we acquired our primary data set, which we worked with. It contained data from around 1,000 patients. These patients had like 2,500 nodules. These nodules were classified by at least 4 radiologists into 5 different classes. So the classes were like definitely benign, maybe benign. The third one was like never know, no one knows. The third one was maybe malign, and the fifth one was definitely malign. So we basically bucketized the two groups on the side. So we had malign and benign categories, and we dropped the category in the middle. And we ended up with a training set of 1,500 nodules and around 100 nodules in our validation set. What you see here is basically, on the first picture, there's a nodule displayed on a basically raw CT scan. The second picture contains annotated nodule. This was done manually by the radiologist. The third one contains the 2D mask of the nodule, and the last picture shows a 3D reconstruction of one of these nodules. So, as I told you, the pre-processing is the most important part of a data science job. So, we firstly had to extract the nodules. So, the dataset we had contained annotation of nodules on each and every 2D slide. So, it was quite easy to extract them and construct the 3D models of nodules. But we wanted to do better than that. We wanted to build a solution. Eventually, yes, it was a neural network to be able to extract and locate these nodules automatically. So what we did was that we used this training data to train a 3D convolutional network to do a rough estimate of what a nodule could be. And then we built another network, which was a simple feed-forward neural network to make the predictions more smoother, so we could actually get very, very good results using our automatic segmentation. Okay, so once we had the nodules extracted and we had our own solution to extract the nodules ourselves, we then had to resample and resize the nodules. So what I mean by that is that, so by resampling I mean that not all of the CT scans came from the same CT machine with the same settings. So we had to put all of the nodules into this shared universal shape. Like different CT machines had different resolutions, so we had to account for it and put all of the nodules on the same level of resolution. And then we had to resize them into one fixed size, because this was later, these 3D models of nodules were later used as inputs for the next 3D convolutional network that was doing the actual classification. But that's not all of that. We also had to to handle some missing values, to handle the low confidence values, which I told you about, and we also had to standardize all of the values. What that means is that we had to, again, put all of the values into some sort of universal representation, like squeeze all of the values between 0 and 1, or express the values as standard deviations from the mean or something like that, so that all of the features would be equal when optimizing our neural networks. Okay, preprocessing is the most important part, so we didn't stop here, and we found a Radiomics library. It was built by some smart guys from Harvard, which allowed us to extract 3 new morphological features and 16 texture features, which improved the accuracy of our neural network by almost 2%, which is a pretty good result because it came like for free. Cool. So yeah, when you start a data science project, you need to have a sort of like baseline for accuracy. We wanted to achieve that in some cool way, so we actually used an AutoML framework called TPOD, which basically builds your machine learning pipeline using genetic programming. This allowed us, gave us the accuracy of almost 89%, which is pretty cool because it's really like fully automated. You just have to do your data cleaning part. This is how it actually looks when it works. And yeah, all of this this whole part of the process is automated by TPOD. You just do the data cleaning, and you get a working Python code as an output, which is really cool. And this is how the TPOD does that. Okay, so once we had our baseline, we wanted to start with simple algorithms that are like that you try as first. So the first one was Adaboost. Adaboost is an ensemble method that basically builds a decision tree which makes some predictions. It looks where the first predictor or the first tree made mistakes. It then assigns higher weights to these parts of the data set, and it creates a new decision tree that is trained on this modified data set, and this goes on and on until you reach your specified number of learners, and then you make the predictions as either an average or as majority vote of these learners. Using this method, we achieved 90% accuracy in classification. The benefits of this algorithm is that it's very fast, it's relatively simple for tuning, and it's basically like a Swiss knife in Kaggle competitions. You can see it often in many winning solutions. And this is what it looks like, basically. On the left side, you can see each individual learner, and on the right side, you can see the wall Adaboost ensemble. Then we reached out to Random Forest, which is a similar method. It actually builds several decision trees or some other weak learners simultaneously, and it lets them learn lets them train on different parts of the data set, and then again you do the majority vote or average for your predictions. The cool part about this is that you can do distributed training, so it's really fast. Again, it's widely applicable, and it corrects the decision tree's habits for overfitting. And again, here's what it looks like. So we had this 4 solutions because we actually had two different results from Teapot. And this is the 5th one. It's actually our best one. It's a classic feed-forward neural network. We constructed 223 training features that were used as an input vector for this neural network. The best accuracy we got was around 92%, which is very good. We built this network using TensorFlow and Keras. Okay, I'm not going to explain how this works, so I'm slowly running out of time. Here's a visualization of basically optimization process. So you start somewhere with a very high error, as the weights of the neural network are initialized randomly, and then you tweak the weights of the network in such a way that you get like lower in this error space. Much more interesting and maybe resource-intensive approach was using a 3D convolutional network. This works a little bit differently from the standard network. It uses a kernel to go through the image data and apply filters to it to learn abstract representation in each and every in the higher or in the deeper layers of the network. In between these convolutional layers, there are pooling layers. Usually, people use max pooling, which works in such a way that once you have your feature map and you want to apply max pooling, so you just take the largest number from the area where you want to apply the pooling, and you get a new basically squeezed feature map. This is done for computational efficiency. Yeah. So now the cool part. So for building these algorithms and models, we used, firstly we started with standard computers that didn't really work well. Then we turned to GPU instances on GCP that worked much better. But then actually we got early access to Tensor processing units on GCP. I think these are now publicly available already, but yeah, we were using them a couple of months ago. This is a really, they offer really a huge improvement either in speed or in price of training your models. So if you're interested in machine learning and you haven't tried the TPUs yet, so just go ahead and give it a shot. As a part of the project, we also built AR visualization of the lungs. This was not done in Python, but I hope you won't kill me for that. And this is what it looks like. So these are the extracted lungs where you can also insert the nodules, which offers which can be used in some obvious use cases. First is communication between radiologists, where they can discuss, I don't know, the patient's condition, or the surgeons can consult with each other before performing an operation. Or the second use case is a communication between a radiologist and the patient. So where a radiologist can easily just visualize that the patient has a tumor and it will expand in such a way, and in the next month it will start pressing on some critical part I don't know, of the heart, for example, and that it has to be removed. I think this level of communication is much better than the current one. So the technology stack we use for building this solution is Keras, Python, TensorFlow, scikit-learn, NumPy, Pandas, Radiomics, GCP, and some JavaScript libraries. What we are about to implement next is actually homomorphic encryption, the way how you can do machine learning on encrypted records of patients. So they don't lose their privacy. We get access to much more training data, which is one of the largest problems in this domain. Doing machine learning in medicine this is the hardest part. Okay, so here's the demo of the application we built. This is a user interface of a radiologist. So here's a list of patients, so you can just view the details of this patient. Here are all of the CT scans that are available for this patient. Here's just one. And this is the diagnosis set by actual radiologist. And these are the outputs of our 5 algorithms. The 3D convolutional network is not there, but that's the job of the front-end guys. So you can see the outputs of our algorithms match the actual prediction. That's not the case in 100% of the records, but yeah, it works in general, in 92% general. And this is actually a 3D viewer of nodules, and this is what an extracted and resized nodule looks like. So the radiologists can actually inspect it and measure it from different sides, and yeah, I think that's pretty much it. But we also have records where our network and algorithms were wrong. Like in this case, when the nodule was benign, only one of the algorithm was correct to predict the benign label. Okay, I think, yeah, I can just sum it up. So what we eventually built was a working end-to-end pipeline where the input is a raw CT scan and the output is a classification for each and every nodule contained in the scan, AR visualization of the lungs and nodules, and visual front-end for all of this. And yeah, that's what's been done. Thank you.
Right, thank you, Daniel. We do have a bit of time for questions, so let me read something from Slido. Which network architecture have you applied? Share your experience, how you have come up with this architecture.
So actually we used several network architecture. As I said, we used 2 networks for nodule segmentation. The first one was a 3D convolutional network, and I think we used UNet as a basis for our network. And the second network was just a standard feed-forward neural network with, if I remember that correctly, 2 hidden layers and a bunch of neurons. But this was just to correct the predictions of the convolutional network in front of it. Then we had again, two networks for classification of nodules. The first one was, again, standard feed-forward neural network, nothing special. We just experimented with several different architectures and configurations until we reached a point where we were just okay with the predictions, and we didn't need to continue trying for better. This was, I haven't mentioned that, but this was actually built as a proof of concept, and it's aimed to be just an assistance system for radiologists. We are not trying to replace them. So just saying. The third network was nothing special, and the third network was 3D ConvNet, but again, we haven't used actually some publicly available architecture for that. We, again, just experimented with 3D layers in Keras, and we again, tried to come up with the best architecture ourselves. Just a lot of trying and some common sense, how you stack the layers one after another.
All right, thanks. And how do you process false positives?
Yeah, so in the segmentation part, that's the goal of our second network. That is actually because the first convolutional network is doing pixel level segmentation, and the second network, the feed-forward one, is just trying to detect the false positives and the segmentation of the first network. So that's how we deal with the false positives in segmentation part, and how we do with false positives in the classification part. Well, we do our best, and we just inform the radiologist of our confidence in the label we have. So when they see that the confidence is not very high, they just might not take this very seriously. Again, this is just an assistance system. So even if there is a false positive, it's not a huge problem, because what would happen is that the radiologist would just check one more like bulk of tissue that eventually would not be a nodule, but that's not really a problem. The problem would be if we actually missed some nodules and the radiologist would do the same. That would be a problem.
Right, thank you. And could I have a very quick answer to the next question? What kind of data augmentation have you performed? Because biomedical data usually comes with a limited number of desired parameters.
So, I mean, if you mean the data augmentation in terms of like creating a more robust data set, so we actually added some noise during the training when we were doing the segmentation. When we were doing the classification, I think we didn't do any extra data augmentation for that. Because, yeah. We used we use a feed-forward network as well as a convolutional network, and the benefit of convolutional network is that they are space and shift invariant. So we didn't have to do a lot of we didn't do any feature engineering for convolutional networks, except actually building the 3D models. So yeah, I guess that answers the question.
Yeah, I think that answers it. So thank you. That was Daniel Kuchta.
Thank you.